dots are my training data sets. So I know that this is a red dot. I know that this is a blue dot. Suddenly, 3 points appear in my figure, right? These stars. Now I would like to predict the color of these stars. Okay. Now the simplest one, in this case, I'm using a machine learning algorithm, nearest neighbor. That is an algorithm. The simplest one is, I pick those stars, I choose the nearest neighbor, and then I color the star with the color of that nearest neighbor. That is called nearest neighbor algorithm. It's very simple. So I determine the nearest neighbors and then change the color into the color of the nearest neighbor. Very simple. Again, it says 0, 1. This time labels are 0, 1. It is two-dimensional. I just show you how data looks like. I have training data set, I have test data set.
What is KNN?
It is the nearest neighbor algorithm. K can be 1. In this case, it is 1. I only consider one neighbor. It can be 3 neighbors, 10 neighbors. So this is the code for one neighbor. I ran a code on this one, right? So again, if you remember from the exercise, right? I'm creating those 4 data sets, training and test data sets. And next thing is I come up with the model. You choose the model. The model we chose is nearest neighbor model. This is a well-known model in machine learning domain. Right? So the name of the classifier that I'm using is K-neighbors classifier. I'm importing. You can go ahead and then check yourself what these libraries are, what they do. I'm just going to point out what we are doing here in simple terms. I am going to be using this classifier, which is the classifier to classify data based on their neighbors. And I create an instance from this classifier. Again, remember, classifier is an object. I turn on this object and create one instance from this object. Now, this KNN is one instance from this object that inherited all the functionalities of this object. Whatever this object is representing, KNN is the child of this object. It is represented. It's inherited. Okay. Now I have trained data set. I have labeled trained data set. I put my trained data set on one side, my label on the other side. I'm referring to these two. This train label data set. And then I fit them. KNN, using KNN, using only one neighbor. I'm running this algorithm here. Okay. One neighbor, the nearest single neighbor. Fit means find the nearest single neighbor and take the color of that nearest neighbor. That's what it means. Okay. The next thing is, what is the success rate of this algorithm on this data set? That is, KNN, again, is this instance which inherits all the functionalities of this object. There are different functionalities of KNN. One is fit, we just used. The other one is score, which we are using now. Score is going to be working on test data sets. I have certain test points that I can throw into this figure. As I throw them into this figure, using that KNN fit, I determine the color of these points, and then I know the real color of these points. They are test labels, and then I compare my predictions with real labels. That is what I'm doing here. Score. My score is 0.77 for this data set. That means 77% of the time I correctly predicted the color of the point falling onto that figure. Is this good? We don't know. Depending on the context, 77% might be very good or disastrous.
How is this calculated?
I'm sorry?
How is this calculated?
This score, it's very basic. You can do this yourself too. Score means I already predicted Y test given X test. How do I predict that? I determine the relationship between X and Y using trained data set. Now I know Y test. I predicted it. And I know the real value of Y test.
Okay.
Then I
Okay,
compare.
no, because you know the real value.
Yeah. Now this is a very simple algorithm. I'm using one neighbor. What if I use more neighbors? In this case, 3 neighbors. Now k and n k equals 3. Now it became a more complicated. Earlier, look at the colors. Blue, I'm sorry, you don't see where I'm pointing. Blue, red, and blue. When I use 3 points, the colors changed. Depending on the algorithm, right, that I'm deploying, the results are changing. That's how I evaluate my model. Now I change the model. A model gives me different results. Okay.
Can you go the other picture? So can you say that again? What was the blue, red, and this stars?
So these are the training data sets.
Okay. So
These are 3 points coming from my test data set. And given the model I'm using, I predict the color of these new 3 points. I know their true colors. I pretend I don't know. Then I'm going to calculate my score.
So those stars are tests.
Yeah, coming from my test data. Later on, once you train this model, you set it up. Not then, data points from outside will come. And then you will determine or predict their colors, given the model.
The training in this case, it means you change the neighbor from 1 to 3 or to try to get a precise output.
That is, so there are 2 training here. I didn't include all that. So you are referring to hyperparameter training. So we are not there. So training here means for when k equals 1. Okay. How can I determine when I get a point? How can I determine the color of this point? There has to be a model that I train. So this model, in this case, is going to find the nearest point first. How? By measuring the distance. So that is how I train my model. Okay. So if a new point comes, you first determine where the point falls into that figure, and then because you have a trained model, right? So you predict the color of that new point. Now, on top of this, you can train your model in terms of adjusting your hyperparameter. What is the parameter here? K should be 1 or 2 or 3 or 10, you don't know, right? So that is the next slide, right?
Oh.
Here. So we used 1, 5, 10, and 30. Which one is better? This is all matter of debate. So for each application, for each algorithm, people have studied all that. So we need to go back and read, and then also do our own research. So let's look at this one. When neighbor is 1, I created these regions in my training data set. If any point falls into this region, that's what training means. If any point falls into this region, I know that it is red. If any point falls into this region, I know that it is blue, because I trained the model. But look at the model. It looks really complicated. There are regions that the boundaries are not clear. Now I increase my number of neighbors. I'm changing the model, the hyperparameter, right? So the boundaries become smoother and smoother. But then I have some errors in my training data set. You see, I predicted these in my training. When I trained the model, I predicted these red dots as blue. Okay. But my model becomes less and less complicated. If you increase this 30 to 40, 50, you'll see that it's going to be a straight line. Just divide the region into two straight with a straight line. Very simple. Now, this is n equals 1 sounds simple, but actually it is complicated, as you see. So that is one trade-off that when you develop your models that you have to work on. How complicated the model should be so that your performance will increase. Okay. So here is this is directly coming from these pictures. N neighbors, then 1 neighbor, then 5 neighbor, then 10 neighbor. Okay. I'm changing x. Axis is giving me the model. K equals 1, K equals 5. And this is the accuracy. So blue is the training scores. This is orange, right? Orange is the test scores. As you see, when n equals 1, training data set performance is 100%. It's 100%. As you see, all the colors are identified correctly. They are within their correct regions, correct colored regions.
That's overfitting, right?
This is overfitting, yes, yes. And given this training data set, now I don't know my, then I test my model on my test data set. As you see, test is not that high because I created those regions based on my training data set so well that it is overfitting. I only considered this training data set. I considered so much that it is fitting perfectly to my training data set, but when a new data point comes into picture, that data point falls into wrong regions. As my model becomes less and less complicated, you don't see the trend very clearly here, but as you see, the performance is increasing. This figure shows better. Small figure. As the model becomes more complicated, the accuracy of your training data set, increases.
So,
Remember, n equals 1 is the most complicated one.
so how do you determine the size of the training set?
Training data set,
Yeah.
so depending on your data, size of the data set, most of the time, the default is 75% to 25%. 80%, 90%. I used, for Blockbuster, I let one movie out, used the entire data set as training, and then predicted this, and then put this data set back, picked another data set outside. So you left one outside and then use the entire data set as training data set. Depends on the size of your data set. If your size of data set is small, I mean, you don't have too much choice, right? So you can, your test data set is gonna be small.
So there is no guideline. I mean, as in statistics, I mean, you can determine the sample size based on the confidence level you want.
Yes. Yes. So here, in this case, I hope I have it in the slides. What you do is you can run a loop, changing your training data sets from say 50% to 90%, and see how the test data set is doing. And then you say, oh, this is the perfect ratio to train my model. So let me go with this ratio.
Usually small companies don't go for machine learning models and all because data analysts can predict what's going on with their customers. So most of the companies who go for machine learning models and like buy some hardware for that is the big companies. They already have big data, like kind of really big. So you have a lot of features, labels, and like, so it's easy to get like 75% is way too much for you to bring.
Yeah.
And most of the companies do that by batches. And once your model is ready, and when you productionize it, you also do the streamline, like real-time streaming training over the weekend. So
Sometimes you cannot handle the data sets. So you sample from the data set and then partition it into training and test data set. This data set is so huge that you don't use the whole data set. So given this model complexity, you remember generalization. From the model, we generalize it, right? As the performance is, as the model becomes more complicated because of this overfitting, your performance is going down in your test data set. So this is the sweet spot here. So you're trying to find the optimum complexity of the model. And it's very easy for machine learning. When I say very easy, just running a loop on a loop and then find the maximum, in this case, accuracy for test data set, and then you stick with that. Of course, you have to keep keep training and then evaluating the model.